So I1 and I2 are basically integers that belong to the same congruence class. The same is the case with J1 and J2. Okay, we have to now first of all prove that addition is well defined. Then, what do we get from these assumptions? Then I1 is congruent to I2 mod n, and like that J1 is congruent to J2 mod n. So from the lemma that we proved after or before defining this, what was that lemma? Have I written it here? Yes. Hence, by lemma 133, we have I1 plus J1 is congruent to I2 plus J2 mod n, and I1 J1 is congruent to I2 J2 mod n. Okay, so this means that I1 plus J1 and I2 plus J2 belong to the same congruence class modulo n, and the same is the case with I1 J1 and I2 J2. Hence, this congruence class I1 plus J1, what is this by definition of this addition? This is equal to the congruence class containing the integer I1 plus J1. But this can also be written like this, I2 plus J2. Why? Because of this congruence. And then again, by using the definition of this addition, this is equal to I2 plus J2. So this shows that no matter which representative of the congruence class I am using, whether I use I1 or I2 or any other thing that belongs to the same congruence class, I am going to get the same sum. This, and similarly I1 J1, this is equal to, by definition of multiplication, I1 J1, which is equal to this I2 J2, because of this congruence, the second one, which is equal to this product of these two congruence classes. Hence, addition and multiplication are well defined. Next exercise 12. Prove the properties (1 through 7) of addition, yes, of addition and multiplication in J. And so these are basically, if you recall, these are the properties that we wrote down, like the ones that we are familiar with: commutativity, associative law, distributive law, those things. Okay, and we don't really have to prove all of them, we just have to understand why they are true. That's how I wrote the solution. We will just maybe show one of them in detail and the others will follow similarly. Solution. We prove only. So anyone we can choose. In this case, all of them follow from basically the same idea. That's why it does not make sense to choose the lengthiest one, which will maybe show you the most complicated proof. It's not like that. All of them are similar. We prove only. So that's why let me choose the first one. Commutativity of addition. Okay, let A and B be two congruence classes modulo and A and B are elements in Jn. Then by using commutativity of ordinary addition of integers, we have, okay, what do we mean by this? So we want to show that A plus B is equal to congruence class B plus congruence class A. By definition, this is equal to this congruence class. Now I already know that ordinary addition of integers is commutative. So in place of A plus B, I can write B plus A. And then using the definition of addition in Jn, I can write like this. So that gives me the fact that this addition in Jn is also commutative. Similarly, you can see that all the other properties follow from the corresponding laws of ordinary integers. That's why we have proved only this one. Okay. Similarly, or let us just write it why that is the case. Similarly, the other properties can be proved by using the corresponding properties of integers. For example, if in place of commutativity you want to prove the distributive law, then the way we have defined addition and multiplication in Jn, they are patterned after the ordinary addition and multiplication of integers. So because ordinary addition and multiplication satisfy distributive law, from that itself the distributive law here will follow. So that's how we will have all the properties. Now we are nearing the end of this list of exercises. I want to finish this because we have been at it for quite some time. Okay, then the next one, exercise 13. These results will be very important when we study ring theory. If A and n are, n of course is a given positive integer, okay, which is fixed. In this context we have to understand that there are many things that Herstein does not mention explicitly. He just tacitly assumes that the exercises are flowing in a pattern. So when he writes a condition like this, you have to understand that he considers n here as the modulus of the relation congruence modulo n. So any condition that any such a modulus satisfies, that is automatically true here. Okay. So if a and n are relatively prime, then prove that there exists an element, yes, B belonging to Jn such that this product is equal to the congruence class containing 1. Okay. The solution is not difficult since A and n are relatively prime. There exist integers b and say m such that, or if you want to be specific, you can write b and m belonging to j. For Herstein, j is the set of integers. B and m such that since 1 is the GCD, it can be written as an integer linear combination of a and n. 1 is equal to, or let me write it the other way, AB plus MN is equal to 1. Okay, so we are coming from that result. Then from this we can easily see that AB minus 1 is divisible by n, because AB minus 1 is minus mn, an integer multiple of n. So, and that can be written in the language of congruences like this. AB is congruent to 1 mod n, which implies this product, which is nothing but AB, is equal to 1. Why? Because AB is congruent to 1 mod n. They belong to the same congruence class. So that's why their congruence classes are same. And it's clear that this belongs to Jn, because B after all is an integer. So the solution ends here. Or if you want, you can mention that this class belongs to Jn. It's trivial, but since you can do that. Now here comes our first problem that is marked with an asterisk. Any problem in Herstein that is marked with an asterisk means that it needs something, some idea that we are not supposed to readily get. We have to work hard to get that idea. There are some problems which have 2 asterisks. Those are problems which, in my experience, they are problems that require something from outside algebra. Okay, some idea from outside algebra. We will come across this type of problems. Many of them are intractable or extremely hard, but some of them can be solved quite nicely. Okay, so asterisk problems, most of them we will solve. Only 1 or 2 I have not managed to solve. But the ones with 2 asterisks, most of them will remain unsolved. However, with the help of many online forums, I have collected some solutions to even those problems. So what this one says is, those of you who are familiar with number theory, they already know this as a form of Farmer's theorem. If P is a prime number, prove that for any integer a to the power p is congruent to a mod p. I hope it is clear. A to the power p is congruent to a modulo p. That's what we have to prove. Okay, so let me start the solution here. In the beginning of the solution, we will make some observations that will reduce our work somewhat. Okay, so the solution goes like this. So first of all, let's consider some cases. Okay, so that means if p is equal to 2, since for any integer a times a minus 1 is even. Why? You take any integer a is either even or odd. A itself is either even or odd. If a is even, then this product is even. If a is odd, then a minus 1 is even. So again this product is even. So it's always even. Since for any integer a this is even, we have a square congruent to a mod 2. Do you see how this follows from this? This means 2 divides a times a minus 1, or a square minus a. That's why a square is congruent to a mod 2. So it just means that the result is true for any integer a and p equal to 2. For that particular prime, the only even prime, the result is true, just like that. This. Again, if a to the power p is congruent to a mod p, then minus a to the power p is congruent to minus a mod p for any odd prime. Or let me write it systematically. Let me not collect the special cases first. Let's just take one step at a time. So what is our conclusion here? So the result is true for any a and p equal to 2. Now assume that p is odd. Okay, p is odd. Also, the result is true for a equal to 0. For 0 it is trivially true because 0 to the power p is actually equal to 0. So in particular it's also congruent to 0 mod p. So this is a trivial situation. And if a is congruent to, a to the power p is congruent to a mod p, then if we multiply, yes, we can multiply. See, what I'm trying to say here is this. What is the meaning of this congruence? It means that p divides a to the power p minus a. Okay, so that means p also divides minus of this, and minus of this means what? Minus a to the power p plus a. Now note that p is an odd prime. So minus a to the power p can be written as minus a whole to the power p. Minus a. Okay. So from this we have this other congruence which has minus a in place of a. What does this tell me? Then, okay, let me just write it here. Then minus a to the power p is congruent to minus a mod p. Note that this is a conditional statement. Okay, if something is true, if this congruence is true, then a congruence like this is true. It tells me that if I prove this congruence for positive a, then for negative a, this is automatically true. So I need to now concentrate my attention only on this congruence where a is positive. So that's what I am going to write. Hence, it's enough to prove this congruence for all positive integers a, because then the negative integers it will automatically follow, and for a equal to 0, because any integer is either positive, negative or 0, that case is anyway trivially true. Okay, now I am in a position to apply induction on a. For me, p is some arbitrary but fixed odd prime number. Okay, that has to be kept in mind. P is odd. So we now, to prove this, we apply induction on a, keeping p fixed. We have assumed p to be an odd prime number that is fixed, arbitrarily fixed. Okay, so now we go for the induction. What happens when a is equal to 1? That case is also trivial. It's easy to see that 1 to the power p is equals 1, so it's congruent to 1 mod p. So this is the basis for our induction. Assume, now we make the induction hypothesis. Assume this. for some positive integer a. This is the induction hypothesis. Now we have to prove this for a plus 1. Okay. Now a plus 1 whole to the power p. We will now expand this using the binomial theorem. Now here there are two choices for us. One is that we can, for binomial theorem, we can refer to my old videos on binomial theorem. But since that is a school level treatment of binomial theorem, what I have written here is that we are going to refer to binomial theorem from Terence-Tao, because the view that I have taken in presenting this is that the Terence-Tao's notes have already been finished. We have already solved all the problems and we have all the results available for us to refer to. With that view, I will now refer Tao's result. It actually appears as an exercise, but nevertheless, so when we really present this result, when it comes in Tau, then this solution will be complete. However, note that in my previous binomial theorem videos, we have already proved binomial theorem. Okay, so I have to write the reference by exercise 714. It's somewhat far away, deep in Tao's book. In the 7th chapter only we come across this, which it involves infinite series. Exercise 714 Tao. We have a plus 1 whole to the power p is equal to, you already know this, it doesn't matter where, from which, from what note or what book you are referring, this the result is after all same. Plus, etc. plus PC, let me write one more, PC P minus 1 A plus 1. 1 is PCP times 1. Okay. And now we make a claim. We now claim that P divides these binomial coefficients. Do you remember binomial coefficients? P divides PCK for these values of k starting from 1 to P minus 1. We have to now prove this claim, okay? Right. Note that, okay, I need to expand this binomial coefficient. For that I need space. Note that this binomial coefficient PCK, where we understand what k is some integer between 1 and p inclusive, p minus 1. So this is p factorial divided by p minus k factorial times k factorial So if we expand this, we will have p times p minus 1 times p minus 2, like this. We will have p minus k plus 1 times, I better write it here, p times p minus 1 times p minus 2. So we are subtracting higher and higher numbers. P minus, let me write it like this, it will become more clear. P minus k minus 1. Then we subtract one more, p minus k. And then if we continue like this, this will be p minus k factorial. P minus k factorial times k factorial. So these two things cancel out, these two factors. So we are left with this p minus 1, p minus 2, p minus k plus 1. This also we can write k times k minus 1, k minus 2, etc. Times 2 times 1, 3 times 2 times 1. Okay. Now we have to prove that this is divisible by p. But there is a question. This is an integer, okay, and that can also be proved using induction or using the properties of binomial coefficients that we have seen when we proved binomial theorem and we solved some problems in those old videos. Okay, so let me write it in bracket. It can be proved that every binomial coefficient is an integer. Okay, I must mention one more thing here. Here we have loosely written every binomial coefficient. Binomial coefficient in this context. There is an extension of binomial coefficients where these things need not be at least this one, this p need not be integer. It can even be a complex number. But we will see those things when we study complex analysis. Okay. So in this context, for us this binomial coefficient involves integers and the value itself is an integer. That can be proved. Okay. So otherwise this divisibility relation has no meaning. No. If this is not an integer, then this relation is meaningless. This must be an integer and this must be a non-zero integer, which it is because it's a prime. Okay. Now, so that is one thing. Now look at this integer. It already has a p. Now it better be the case that this denominator, this integer, divides this part. Okay? That's what we have to prove. Because otherwise, if p cancels out from this part, this denominator, if p appears in the denominator and somehow these two cancel out, then we don't have any p here. In that case, p will not divide this. So the argument goes like this. Since k is less than or equal to p minus 1, which is less than p, p does not divide this product. Why? What have we written here? K is an integer, k is a positive integer strictly less than p. Okay. That means all the numbers that you see here, k, k minus 1, k minus 2, all of them are strictly less than p. And obviously none of them is divisible by p because they are less than p. So p cannot divide their product also. Why? Because you see, we are using that corollary to that one result, which says that if a prime number divides a product of some integers, then it has to divide at least one integer. In this case, that is not possible because all of them are less than p. So that's why p does not divide this. Now that this part is clear, from this we have another conclusion. Hence, p and this number, which is nothing but k factorial, but anyway, since we have written it in this expanded form, let me just continue writing it like that. So that's why these two numbers are relatively prime. Why? You see, just now we have proved in one exercise that if n is a prime number, then for any integer a, we have either n and a relatively prime or n dividing a. Now for us, in place of n you think of p. For us p is a prime number, we already know that. And for in place of a you think of this k factorial. Now p does not divide k factorial. So that means this must be true. P and k factorial are relatively prime. So these two are relatively prime. Okay.